Welcome to the last lecture on important cuts. So in the first two lectures or first three lectures you saw about important cuts, and in this we will use this to give another algorithm for one of the most important problem in parameterized complexity, whose parameterized complexity was an open problem for long time, and that was directed feedback vertex set. Edge set. Okay, so that will be a goal to design an algorithm for this. Okay, but before that, let's just revise some of the topics that we covered in the previous lectures. Was that what we did first was that we defined this notion of delta R, which was basically a set of edges with exactly one endpoint in R. Then we talked about minimal XY cut, which was nothing but it's a set of edges such that there is no path from a vertex in X to a vertex in Y, and no proper subset of S does this job. Meaning, if you only delete a proper subset of edges of S, then there will be a vertex in X, there will be a vertex in X, and there will be a vertex in Y, such that there will be path. And an important observation was that for a minimal edge cut, I can find a set R such that S is nothing but delta R. Okay. And what extra property is this, that X is contained inside R and R intersection Y is empty. Okay. And so for example, look at these four edges. These are like edges emanating out of R. Then we define this notion of important cut. And what was an important cut? A cut was important if there was no other cut which dominated it. And what do I mean by this? A cut is called a minimal XY cut is important if I cannot find another XY cut with the property that it covers more vertices than R, and number of edges that are leaving R prime is lesser or equal to the number of edges that leaving R. For example, look at this cut R. Is it an important cut? And we also showed that we can actually test whether a particular cut is important or not in polynomial time. Okay. So the question was, is this cut important cut? And answer was not, because you can find an R prime which has as many edges leaving as R. So for example, there were 4 red edges, we have 4 blue edges, but it contains R and also contains some other set of vertices. Okay, so this particular R was not an important cut. But you look at this R and look at these 3 red colored edges, you can show that you cannot find any R prime which contains R properly and has at most 3 edges leaving it. So any other vertex you will put inside, it will have more number of edges going out, which implies that this particular R is an important cut. And then we had this important theorem which showed that there are at most 4 to the power k important XY cuts of size at most k. Okay, and this was very useful because we could use this important cuts to design an algorithm for a problem called a multi-way cut. So what was a multi-way cut? So multi-way cut of a set of terminals T is a set of edges such that each component of G minus S contains at most one vertex of T, or alternatively we can say that for any pair of vertex in T, there is no path after we deleted the edge set S. And it is, as I told you, that if you just given 2 vertices S and T, then this is polynomial because it is nothing but a min ST cut problem. But the problem was already NP complete for fixed number of terminals T greater than or equal to 3, and that is why we told that we do not expect to have an algorithm of this nature. In fact, we do not expect to have an algorithm for this nature unless P equal to NP. Okay, but if you recall correctly, we showed that it is trivial to solve the problem in polynomial time for fixed k. You just try all possible k size subset and check whether it is a multi-way cut or not. But we designed an algorithm using important cut with running time 4 to the power k n to the power 1. In fact, we didn't design this algorithm. We talked about this algorithm, but the running time which we properly analyzed was 16 to the power k n to the power of big O of 1. But that algorithm can be made to run in 4 to the power k polynomial in n. Okay, so this was a slight this is a slight covering of whatever we did previously, and now let's see what we do. And here's your algorithm. So recall, the heart of an algorithm was the following pushing lemma. What was the pushing lemma? It says that look at any solution. It definitely disconnects t from all other terminals by some set of minimal cuts, which is contained inside my solution. But what we showed that, well, it is not any minimal cut, but we can find a solution where this minimal cut can be replaced by one of the important t minus t cuts. The moment we got this very interesting algorithm that basically said, if every vertex t is in different component, then you are done. Else, you pick up a vertex which is not separated from a vertices in t minus t, you enumerate one of the important cut of size at most k, delete this and recurse with a new parameter k minus cardinality of state. Okay, and first, it's very trivial to design a 4 power k algorithm for this problem, 4 power k square, because in each branch, because the budget is decreasing by 1, the depth of the tree is at most k, and since each branching factor is 4 to the power k, the total running time is algorithm 4 to the power k square. But then we use a refined analysis to give 16 to the power k algorithm, but that algorithm can also be analyzed even more carefully, and we can get a 4 to the power k algorithm for the problem. Okay, so that was the state of affair till the first 3 lectures, and let's see what do we. So the first problem that we are trying to talk about today is what is called multi-cut problem. So what is a multi-cut problem? So unlike multi-bay cut problem, you are not given a set of terminals, but you are given a set of request pairs, which are called S1, T1, SLTL, and you are supposed to delete at most k edges with a property that after you delete this, there are no paths between Si and Ti for any I. And why did I use the word that multi-cut generalizes multi-bay cut? Because given a graph G and a set of terminal T, we can create a request pairs by, for every Ti Tj in T, I not equal to G, you would create a request pair Ti Tj. And what does that imply? That now you have reduced multi-bay cut to multi-cut type. You put up each request physically rather than giving a set of terminals. And okay, and now what I'm going to show to you is an interesting algorithm. So let's see how we can solve about multi-cut. So basically, imagine that you have this set S and you have S1, T1, SLTL pair. Once you delete this, maybe there is a connected component which contains S1, T3, S2, S4, T5, T7, so on and so forth. So after I delete this, the set of terminal pairs S1, T1, S2, TL, SLTL gets distributed. But once this gets distributed, and this is your green color or your edges of S, what is the property of this? So if I think of this set of S1, T3, T2 as a subset of vertices, then my edges of S actually acts like a multi-way cut. Okay, fine. So this S is basically a multi-way cut of this set of, this set of terminals here, each of this. So that immediately induces a partition of the set T star, where T star consists of S1, T1, S2, T2, SLTL. So, what do I do? So after I delete the edge of S, the terminals in T star gets partitioned into different connected component. So my algorithm is going to be, you guess a partition of T star. Suppose they are T1, T2, TQ. It's a partition of T star. Now you first check, is this a valid partition? Meaning, if I delete the solution set S, can we get this partition? What is the meaning of that? Si, Ti should not occur in the same part. Meaning, they should not be in the same part. Because what we are trying to do is to disconnect every vertex in Ti from every vertex in Tj, but we are not caring about disconnecting vertices in the same pair. That is the model of describing this Ti. Now we are going to identify Ti into one vertex, and which is very simple. You delete vertices of Ti, add a super node, say Ti, okay, and make him adjacent to every vertex, any vertex in Ti was adjacent, right? So now for these super terminals, what you are going to run? You run your multi-way cut algorithm. But then what is your running time of this algorithm? Because you know that at least one of the guesses is correct, and for that, if you run this multi-way cut algorithm, then it should partition them into different parts of with at most k. So the running time of algorithm is guessing the partition, okay, guessing the partition, which is L to the power L, and then running this 4 to the power k algorithm, which means that we can solve the multi-cut in FKL n to the power big of 1 time algorithm. Okay. So how did we solve multi-cut? But we solve multi-cut by reducing it to a multi-way cut parameterized by k plus 1, k plus L, and this is how you show this theorem. Okay, that multi-cut, which is a extreme generalization of multi-way cut, is FPT parameterized by number of request pairs as well as the solution size. So what are the natural question to study then? So the natural question to study, this is just one line proof for whatever we have been talking about. So the one line solution is that what about parameterized by just k? Well, multi-cut is FPT parameterized by the size k of the solution, but unfortunately that requires much more tools and techniques than just important cuts, and hence we will not be covering this in this course. Okay, but I must insist, or I must mention that it also uses the idea of important cut very crucially, but it also uses much more advanced tools than just important cuts. Okay, however, we will take a slight turn, and what we are going to do is we are going to generalize the notion of important cuts to directed graph. So it's a very natural direction. So because we are talking about directed graphs, we have all kind of edges that will leave some set, or edges which we must be getting inside this set. Given on this, you know that you have a notion of out neighbors, in neighbors, okay, and so you can define delta out neighbors of set R, delta in neighbors of set R, but we will develop our theory with out neighbors only. Okay. Okay. So what is a delta R? Is a set of edges leaving R, and as for undirected graph, we can show that every inclusion minimal directed XY cut S, and by directed XY cut S, meaning you want to delete path from a vertex X in X to a vertex in Y, but you are not caring about deleting a path from a vertex in Y to a vertex in X. Okay, then you can actually, if you want to cut, then you can come up with a notion of S can be represented as arcs which are leaving a set R. So for example, this set R is a valid out arcs, and then you naturally and of course X is contained inside R, and R intersection Y is empty set. Okay. Okay. Of course, there's a natural notion of extension of important cut. What is an important XY cut? An important XY cut will be a cut which is not dominated by other XY cut. What is the meaning of this? I should not be able to find another delta R prime or R prime with a property that the number of out arcs from R prime is lesser or equal to R, and R prime properly contains the set R. Okay, this we should not be able to find. So you ask yourself, is this R that we have drawn is an important cut? Well, no, because you can come up with an R prime that properly contains a set R and has at most as many edges leaving R prime as it was as R. So in R we had 1, 2, 3, 4 red edges, but in R prime we have 3 blue edges. So R is not an important cut. But what about R prime? What about R prime? R prime is an important cut. The moment you try to extend R prime by taking any other vertex, number of edges leaving that set will be more than 3, and hence that is not an important cut. Okay. Okay. So the proof for the undirected case also goes through for directed case, and you can show that there are at most 4 to the power k important directed XY cuts of size at most k. And how do you go about doing this? Exactly like an undirected graph. You show that delta hat is some modular function. Min cut is again equal to max follow for directed graph. You define R max with respect to min cut lambda like extension. Then you show that R max is contained inside every important cut in directed graph, right? So it's a very, very good exercise that you go back, look at each of the undirected lemma we proved, and extend it to the notion of directed important cuts or directed min cuts the way we have defined here. Okay. The moment you have this R max, the algorithm becomes very same. You start with R max, you look at the edges which are leaving it, say UV. So either the UV is part of the important cuts you are thinking, then you delete UV, you decrease k by k minus 1 and recursively find all the important cuts of size at most k minus in G minus UV. Or you know that UV is not, then you extend X by including V in, and you will look for all important cuts of X union V and Y. But because R max is there, if you look at any set which contains R max, the min cut from there to Y is larger than lambda. So in this case, though k remains the same, okay, k remains the same, lambda increases by 1. And so if you look at the same measure mu 2k minus lambda will drop in both cases, right? And hence you can show that the number of important directed cuts are upper bounded by 4 to the power k. Okay. So as again, it's a very important exercise to go back to every lemma of undirected graph, apply with this new notion of directed cuts and check that it works. Okay. Okay. So suppose I wanted to solve not undirected multi-way cut, but directed multi-way cut. So what is a directed multi-way cut? So in the directed multi-way cut, you are again given a directed graph G, a set T and K, and you want to delete K vertices so that between any pair of vertices in T, there are no directed path. But notice that when it was an undirected graph T, if you have two vertices U and V in T, then deleting a path from U to V is same as V to E. But in directed graph, it is not same, right? You have to kill paths from U to V as well as kill paths from V to U, right? So now I'm going to show to you that, so the main crux why the undirected multi-way cut algorithm worked is that, look, any cut must disconnect T from T minus T by some minimal cut, but we can replace that minimal edge cut from T to T minus T by an important T minus T cut. But we will show in a minute that such an object is not possible to show for directed multi-way cut, and hence we cannot apply just an important cut algorithm and hope that it will work out perfectly fine. So look at this instance of directed multi-way cut. S to T, we have to disconnect from S to T. So there's a unique solution with k equal to 1 edge. That is deleting the edge AB, right? But what happens? Look, so this solution is given by the arc set SA. But it is not an important cut because boundary of SA is this R, but the boundary of SA and boundary of say SAB has the same one edge cut. So definitely SAB is SA is not an important cut because SAB dominates it. But like if you delete this blue edges, is not part of any solution of size at most 1, right? Because there's a unique solution of size at most 1. But then you may ask, why is it failing? So if you just try to look at the undirected graph lemma and try to mimic the proof, you will be able to see why this proof does not work. Okay, so how did the proof work? So you say, look at T minus T, look at all the vertices which are reachable from T, let's call that R, okay, these are reachable vertices. If if R is not an important cut, then there is another important cut R prime, so let's extend it. And what you did, the way you created a solution is that from S, you deleted delta R and added delta R prime. Now, and then you argued that this also is a solution, but we have to be very careful. It is indeed true that there is no directed path from T to any other vertices in T minus T, but nobody stops from having a path from some U using, like I could have a path from U to T, right? How? Because, I could have a path from U to some other vertex inside R prime or R, and since R is a reachable, because any such path must contain red edges, but the moment it will contain a red edge, you can jump into R, and from there because this vertex is reachable from T, you can find a path from here to here and you can reach, but create a UT path, right? I'm like, I mean, this is not right, but what I'm saying that it could possibly happen that I can jump from U to this and U to this. I can come inside R because of the backward arc, and from there I might be able to reach T. Okay, it is possible. I may not be able to reach, but I might also be able to reach, and that will violate that S prime that you have constructed like this is a solution. It is indeed possible to show that directed multi-way cut is FPT parameterized by size K of the solution, but it requires again additional set of techniques which is very similar to the techniques we need for undirected multi-cut, but again it is beyond the scope of this course, so we will not talk about it. Okay, what about directed multi-cut? Okay, so what is a directed multi-cut? Again, it's like a undirected multi-cut. You are given a directed graph T, you are given a request pair S1, T1, SL, TL, integer K, and you need to delete set of edges so that G minus S has no SITI path for any. If you notice, this also generalizes directed multi-way cut as again, because for a set T, you write all possible pairs like unordered pairs as a request pair, and that is an instance of directed multi-cut, and then you are done. But Marx and Rajgon showed, Marx and Rajgon showed that directed multi-cut is in fact W1 hard parameterized by K. What is the meaning of this? It is just mean that we do not expect to have an algorithm with running time f of K poly in N. That's all that it means. So whenever you see W1 hard, W2 hard, W3 hard, it just means that you should not expect the problem to be fixed parameter tractable parameterized by the parameter in which the problem is shown to be some W hard. We talked about this little bit in our first lecture, and we will cover this in detail in the last week of our course. Okay. So directed multi-cut is W1 hard parameterized by K. Of course, we cannot expect the problem is FPT just parameterized by L, because even for L equal to 2, the directed multi-cut problem is W1, is NP complete, I'm sorry. But what about the case L equal to 2, right? What about directed multi-cut when the number of request pair is constant, or we can use number of request pairs to be a parameter? What happens then? So L equal to 2 actually can be reduced to directed multi-cut. So you have like, you want to kill all the paths from S1 to T1 and S2 to T2. What you do, you add 2 additional vertex X, and you add an edge from X to S1. So basically, and T1 to Y. So basically, this is trying to capture all the paths from X to Y, and you add TT to X, an edge, and Y to S2, and this is trying to capture path from Y to X. Okay, and you can show that directed multi-cut is equivalent to directed multi-way cut with terminal set being XY. Okay. So it's a very simple reduction or this thing. Please try to do it yourself. Okay. But so what does this mean? That for what then the natural question that will arise, what about directed multi-cut with L equal to 3? What about directed multi-cut? Is directed multi-cut FPT parameterized by K and L? And there was a recent progress, not recent progress per se, but like roughly in 2016, Philip and Wallstrom showed the following. The directed multi-cut is W1 hard even when you have L equal to 4 terminals. So what does it imply? It immediately implies that you cannot have an algorithm parameterized by F, K, L, because that will imply FPT for L equal to 4 case. However, when L equal to 3, it is still unknown whether the problem is FPT or W1 hard. So this problem still remains open, right? So what is the parameterized complexity status of directed multi-cut when the number of request pair is upper bounded by 3? Okay. Okay. And of course, if it is like all the 6, like this is like one of some of those cases are definitely FPT because of the directed multi-way cut. Okay. Great. So that led to the study of directed multi-cut on DAGs. So what is DAGs? So DAGs are basically directed graphs with no directed cycle. So for example, like This is not a DAG. This is a DAG. Although it's an undirected sense, there's a directed cycle, but there is no directed cycle in sense of directed graph. So it is known that directed multicut is actually W1 hard parameterized by K even on directed acyclic graph. Directed multicut is NP hard for L equal to 2 on directed acyclic graph, and directed multicut is FPT parameterized by K and L on DAG. So it was shown that though directed multicut may not be is W1 hard on general digraphs parameterized by K and L. In fact, even for L equal to 4 terminals, it is W1 hard, but it is FPT parameterized by K and L if we take directed acyclic graph, a graph that does not contain a directed cycle. So extending this algorithm to other classes of digraphs is an interesting open problem. Okay, but here's a very interesting special case of directed multicut, which is called skew multicut, which has been an extremely useful algorithmic tool in directed graph. So what is a skew multicut? So in a skew multicut, you are given a graph G, you have pairs S1, T1, SL, TL as before and integer K, but you are looking for a directed edges such that G minus S contains no SITJ path for any eigenvalue. What is the meaning of this? So basically what I mean to say is that, look, if you have S1, S1 should not have path from S1 to T4, T3, T2, T1. Similarly, S3 should not have path from T3, T2, T1, but S3 could have a path from T4. So basically what it means that if you look at the SI, then SI should not have a directed path to any TI whose index is lesser or equal to the SI, right? But it doesn't care about killing paths to higher indexed guy. That's important point, right? So S4 must, like we are looking to delete set S of edges so that there is no path from S4 to T4, T3, T2, T1, S3 to T3, T2, T1, but S3, T4 path, maybe they are disconnected or maybe there is one. We do not care. Okay, so this is what skew multicut is. So I would request you that you pause this video for a couple of minutes and absorb the definition of skew multicut properly. Okay, so recall what was the main reason undirected multicut was FPT, because we were able to show to you that you fix any terminal and fix other set of terminals, then there exists a solution that contains one of the important S T minus T cut. Now I cannot show this for any SI and the set of requests it needs to care, but I'm going to show to you that at least the following statement is true. The skew multicut problem has a solution S that contains an important SLT1TL cut. What is SL? SL is the highest indexed vertexes. So SL needs to kill all the paths to all the TIs. That's important, right? I'm saying to you that, look, this must contain an important SLT1 to TL cut. Suppose we prove this lemma, then also we will be able to design an algorithm for skew multicut. How? Because rather than picking any arbitrary terminal, we'll pick a terminal which is highest and which still needs to be disconnected from everybody else. So you rather than starting from anything, you will first take SL, try to disconnect from everybody else. Then when the job of SL is done, you pick up another, then you ask for SL minus 1. Hey, are you disconnected from whomever you wanted to? If yes, then you move on to someone else. But so you pick up the highest SI which is still connected to one of the TIs that it needs to be disconnected, and you try to disconnect those. Okay, that's the point. Okay, so let's try to prove this lemma. Okay, and the moment we are able to show this, we will be able to get an algorithm with running time 4 to the power k poly in n for skew multicut. Let's see how we go about this. It is exactly similar to the undirected pushing lemma. So let R be the vertices reachable from T in G minus S for a solution. What happens? Either R is an important cut, or R is not an important cut. R is important cut, then you are good. then if R is not an important cut, then what can we say? If R is not an important cut, then there exists some R prime which strictly contains R, disjoint from T1 to TL, and delta of R prime is at most. So now you create another S prime, you remove delta R and you add delta R prime. Clearly, you removed some set of edges and you added some set of edges, but the number of edges that you added is smaller than what you removed, which implies that S prime at least cardinality bias is perfectly fine. Now, why is this not a solution? Suppose this is not a solution. What is the meaning of that not a solution? So definitely, SL gets disconnected from T1 to TL even in G minus S prime. But what could happen that now you might get a path from SI to TI for some SI TI. Okay. Why? But look, when I deleted red edges, it was still like when I deleted S minus, when we deleted S, it was a solution. I mean, there was no SI TI path, whatever path you need to cut, but suddenly you have got a path. It means it must be using a red edges. If it must be using a red edges, it must be using one of the red edges. It means that path from SI to TI must be coming inside this R prime, or in fact in R. But what is the property of that vertex in R? SL, this vertex is reachable from SL. It means there is a directed path from SL to this vertex. Then I can get a path starting from, you go to SL to V. Now on this SI TI path, you follow the path from V to TI. So what you have been able to achieve, right? You will get a SI TJ path implies a SL TJ path. But you know that in G minus S prime, there is no SL TJ path, right? And this is where we use the fact that SL is the largest integer, because SL needs to disconnect itself from each of the TI. So existence of any SI TJ path implies SL TL path, which also my S prime needs, which also S prime takes care, and hence S prime is a solution. So this is how you can show that. So this immediately implies the following algorithm. For this, let you fix an SL. The skew multi-cut has a solution S that contains an important S T1 to TL cut. And if so, rather than having if every vertex, like if every request pair is taken care, then we are done. Else you choose the largest terminal that need to be separated from T1 to TI, branch on a choice of S1 to T1 TI, important cut of size at most K, delete that, recurse, and this. So this will give you a 4 to the power K algorithm for search tree, and that's it. So that implies a 4 to the power K algorithm for skew multi-cut. Okay. So this gives us a 4 to the power K algorithm for skew multi-cut. Why do we care about this? Okay. We care about this because it allowed us, or it helped us resolve the parameterized complexity of one of the most important open problem in the area about directed feedback vertex or edge set. So what is directed feedback vertex or edge set? So this is a counterpart of let's say this is a counterpart of undirected feedback vertex set. So what is this? So directed graph G, integer K, and you have an objective of deleting K vertices or edges such that G minus S is acyclic. It is known that the problem is, what is that called? It is known that the problem is FPT, like not FPT, but it is known that the edge version and vertex version are equivalent. What I mean by this? So let's say directed feedback vertex set reduces in a parameter preserving way to directed feedback edge set, and directed feedback edge set reduces in parameter preserving in directed. The reductions are fairly simple. So let me tell you, the first one is basically based on the following fact that you look at any vertex V, right? So you make V in, V out, and make every vertex which has in neighbor, say A to V in, and every out neighbor you make from V out. Now you can show that if you have a K vertices, if and only if there are K arcs, and the arcs which you will form in your solution are these arcs. Okay, you should be able to see. And for the second one, what is known as line graph. So I will leave that and I will ask you to check. So in directed graph, these two problems are equivalent, which is not the same in undirected graph. In undirected graph, if you want to delete edges, it is nothing but just finding a maximum forest, or basically, yeah, you find a forest, you have to delete everything else. So while edge version is polytime, vertex version is NP complete in undirected graph. So, but for directed graph, these two problems are basically same. By you can come up with the splitting operations. Okay. This is the first problem where we will apply more than one tool to solve the problem, and we are going to solve the problem by applying iterative compression. So what is going to be iterative compression? We are going to assume that you are given some k plus 1 edges such that g minus s is such that g minus s is acyclic. It's easier than the original problem as the extra input w gives us useful structural information about g. So we are going to show that the compression problem is FPT parameterized by k. So let's reread the problem. You are given a set w of k plus 1 edges, g minus w is acyclic, a set of k edges g minus s is acyclic. So the moment we will be able to solve this problem, the moment we will be able to solve this problem, the moment we will be able to solve this problem, we will be able to solve directed feedback. Now you may say, from where are you getting this k plus 1 edges? So if you recall correctly, for the compression algorithm, we were having this vertices v1 to vn, and we took the first I vertices, look at the graph induced on that, so on and so forth. But now we will build this graph one arc by each, and the moment we will add one arc, we'll say, hey, right? So then you can, if the smaller graph has a solution of size at most k, then that's correct. You added the k plus 1th arc and that will give you w. But we will do this formally. But for now, just assume that you are given a w. How can you solve this problem? Okay. In fact, we are going to not assume, right? In fact, we are going to assume that what we are given is k plus 1 vertices as a g minus w is acyclic, and we want to find out k edges as a g minus s is acyclic. And this is a useful trick to have for edge relation problem. You define a compression problem in a way that the solution of k plus 1 vertices are given, and that is very easy. All you need to do is that look at this k plus 1 vertices, just pick one vertex each from this k plus 1 edges, and then if you delete it, these edges are taken care of, and hence that forms a solution for many problems. It's not always true, but for many problems, this trick will help you to reduce that you are not given an edges, but you are given a set w, and you try to bring your compression problem with respect to help. So the way to look at iterative compression is that the extra set w is like a help, or it provides an extra structure to our problem, can be exploited that structure to design our algorithm. Okay. So before we go further, let me tell you what was a DAG. A DAG is a digraph that does not have any directed cycle. And what is an equivalent definition? That D is a DAG if and only if there exists a topological ordering of D. And what is the topological ordering? It's basically a permutation of vertices such that every arc goes from a small index vertex to the higher index vertex. Okay. And and so these arcs are also called, you must have seen, these arcs are also called forward arcs. Okay. But if I give you a normal digraph, then it cannot have an ordering so that every arc is forward. Then some of the arc may be going from higher to lower, and these are called backward arcs. Okay. So if you are looking for G and we want to delete at most k arcs as G minus S is DAG, then basically what we are asking is that can we find a permutation pi such that number of backward arcs is upper bounded by k, right? So this automatically gives us a very simple algorithm which is like n factorial. You look through all permutation and check if there is one permutation with at most k backward arcs going. Okay. Now it's an n factorial algorithm. But what we are going to do is that we are going to exploit this to design not n factorial but a FPT kind of algorithm. But we will take this view of feedback arc set, that give me a permutation of my vertices such that the number of backward arcs is bounded by k. So now, this is what you are given W1 to Wk plus 1. Okay. Okay. So we will talk about the splitting later. But I said, look, if there is a solution of size at most k, then what I mean by this, okay. So we guess the permutation of W in G minus 7S, right? Then I know there exists a permutation. I cannot guess all the vertices, but I can guess how the vertices of W are ordered on them. So this is like a k plus 1 factorial. Okay. Now, once I have achieved this, okay, this is what I have guessed, okay, that maybe there are some vertices here. I don't know what these vertices are. Only thing which I am guessing is W1 comes before W2, W3, Wk plus 1. Look, if the vertices of W are named W1 to Wk plus 1, it may not be that this is the right permutation. But I mean, you can assume that suppose the permutation is W5, W7, W9, then let's pretend W5 as the first vertex, W7 as the second vertex, so on and so forth. Okay. Once you have done this, you do the following trick of splitting. The way when we made our reduction some time back. So what you would do is, so suppose Wi has an in arcs from A and B, then you make Ti and Si, give an arc from Ti to Si, make A adjacent to Ti, make B adjacent to Si. Why are we doing this? We are trying to move towards giving a reduction to our skew multicut. You will see in a minute. Okay. So what is our claim? Our claim is G minus S is acyclic and has an ordering with W1, W. That implies S covers every SITJ path for every year. So if G minus S is acyclic and this particular ordering, then S must intersect. So, okay, let's see. And suppose I deleted S, G minus S is in ordering, and this is this. Then why does S covers every TITJ path? Let's see. Okay. Look at G minus S is acyclic. And so acyclic, and so look at G minus S. It is acyclic, so it has an ordering of vertices, of all the vertex, okay? Not only this. And W1 is here, W2 is here, W is like, this is, which is like this company. Now, I'm claiming to you, there is no path from Si to Tj for every I greater than or equal to 0. Okay. What is the meaning that I have a path from, right? So, think of this way, this Wi, I can write it, I can replace this Wi with S1, no, sorry, T1, S1. Right? And you will notice that this DAG property still holds. T2, S2. So on and so forth. Right? So you replace Wt by their T2, S2 and make every in neighbor coming to T2. Now, what is the meaning? And look, still this is. So what is the meaning that I have a path from some Si to Tj where j is less than or equal to I? Let's just try to ask ourselves. It means I start from here and say Tj is somewhere here. I can only go forward. I do not have a backward arcs. So definitely S has killed all the SITJ path. That's it. Very simple. Because there are no backward arc. Okay. So this is very simple. And now suppose you are given this instance of SITI and S covers every SITJ path for every I greater than or equal to 0. Then I claim to you G minus S is acyclic. And that's also very, very easy. Why this is very easy? Because if J minus S is not acyclic, then fix some W there. But remember, W is a directed feedback vertex set. So if it is not acyclic, there is a cycle and that contains a vertex wi. If it contains a vertex wi, then you replace wi with some SITI, right here, SITI. And then you go along, and wherever you see, so what I mean to say is that, okay, what do you mean by this? So look at this. So maybe here just cycle, and suppose this is wi, wj, wk. Okay. So you replace wi with, suppose this is how it is. Then you replace wi with ti, si. That's it. Similarly, wj by tj, sj, and you get a cycle like this. But it is also a path in this graph from si to ti. But there is no path from si to ti. This is what you have assumed, right? This is what you have assumed, that there is no path from si to tj for every, which implies g minus s is acyclic, right? So that's it. So we have shown an equivalence. So what is our algorithm? Our algorithm is going to be very, very simple. Guess the ordering, split the vertices, and then call skew multicut problem instance, right? So we can solve the compression problem by k plus 1 factorial application of skew multicut, right? So you guess the permutation, you split this, I say, hey, now this is my skew multicut instance, give me a solution, okay? And then you are done. But as I told you, so we have given an f of k poly n algorithm for the following compression problems. You are given a set of w of k plus 1 vertices, so the g minus w is a cycle. How do you get such? So now we will get it for free. Iterative compression, we have seen it several times, but let's just do it once more. So now we will let v1 to vn be the edges of g, and let gi be the subgraph induced by first I. So what I'm going to do, for every I equal to 1 to n, we find a set si of at most k edges, g minus si is acyclic, and then do as follow. For I equal to 1, we have the trivial solution si equal to 5. Suppose we have a solution si for gi, and let wi contain the head of each edge of si. Then clearly w1 union vi plus 1 is a set of at most k plus 1 vertices, whose removal makes gi plus 1 acyclic. Use the compression algorithm for gi plus 1 with the set wi union vi plus 1. If there is no solution of size k for g plus 1, then g does not have a solution of size at most k. You are done. Otherwise, compression algorithm returns a solution si plus 1 of size k for gi plus 1, and you repeat. So you repeat this algorithm n times, and everything else is polynomial. Okay. So directed feedback edge set is FPT using iterative compression. So you saw, we started with a multi-way cut algorithm. We tried to generalize it. We couldn't generalize it to either undirected multi-cut or directed multi-way cut or to directed multi-cut, but we were able to find another something called skew multi-cut, and we were able to generalize that to generalize our algorithm to that. And once we were able to do that, we were able to show that one of the most important open problem in the parameterized complexity can be shown to be FPT using this algorithm. Okay, so what we have seen in this week is definition of important cuts, combinatorial bounds on the number of important cuts, pushing arguments for that we can assume the solution contains an important cut for multi-way cut, skew multi-cut, and then we use iterative compression to reduce directed feedback vertex set or edge set to skew multi-cut. And so there's another technique called randomized sampling of important separators, which is there in the book, but we will not be covering in this course. So I request you to, or maybe we will do that in the next version of this course if ever we do. So thank you. I think with that, we will end this week lectures.